Hello everyone, I'm Professor Diwa, and welcome to a math video on inverse functions. Our objectives are to determine whether a function is a one-to-one function, use the horizontal line test to determine whether a function is a one-to-one function, find the inverse of a function, find an equation of the inverse of a function, graph functions and their inverses, determine whether two functions are inverses of each other. Alright, so let's get started. First, we have the definition for a one-to-one function. It states here, for a one-to-one function, each x value, which is an input, corresponds to only one y value, which is an output. And each y value, the output, corresponds to only one x value, the input. Notice here that the first part of the definition for a one-to-one function actually contains the definition for a function. It states here that each x value corresponds to only one y value. That's essentially the definition of a function. The second part of this definition states that each y value corresponds to only one x value. That second part of the definition is what makes a function a one-to-one function. We're going to use this definition in the next example to determine whether each function is a one-to-one function. In example number 1, determine whether each function described is one-to-one. For part A, we have the function f, which is equal to the set of ordered pairs 6, 2, 5, 4, -1, 0, and 7, 3. To determine if this function is one-to-one, we just need to make sure that each y value corresponds to only one x value. So 2 corresponds to 6, 4 corresponds to 5, 0 corresponds to -1, and 3 corresponds to 7. So each y value corresponds to only one x value. That means that the function f is a one-to-one function. Moving on to part B, we have the function g is equal to the set of ordered pairs 3, 9, -4, 2, -3, 9, and 0, 0. Again, we just need to check that each y value corresponds to only one x value. 9 corresponds to 3, 2 corresponds to -4, 9 corresponds to -3, and 0 corresponds to 0. So this function here is not a one-to-one function because you could see here that 9 corresponds to two different x values, -3 and +3. For part C, we have the function h is equal to the set of ordered pairs 1, 1, 2, 2, 10, 10, and -5, -5. We could see here that each y value corresponds to exactly one x value. 1 corresponds to 1, 2 corresponds to 2, 10 corresponds to 10, and -5 corresponds to -5. So this function h is a one-to-one function. For part D, the inputs are minerals, and the output is the hardness on a scale. We have talc corresponds to 1, gypsum corresponds to 2, diamond corresponds to 10, topaz corresponds to 8, and stibnite corresponds to 2. This is not a one-to-one function because the output of 2 corresponds to two different inputs, gypsum and stibnite. For part E, we have a graph with several points plotted. We have one point at -3, -3. We have another point at -2, -1, another point at -1, -1, another point at 0, 0. We have a point at 2, 1, and one more point at 3, -1. This graph of points would not represent a one-to-one function. If we take a look at these 3 points here, we have -2, -1, -1, -1, and 3, -1. These 3 points here have a y value of -1, which corresponds to 3 different x values, -2, -1, and +3. For part F, we have cities for the input, and then for the output, we have percent of cell phone subscribers. For the first city, we have Atlanta corresponds to 75, Buffalo corresponds to 53, Austin corresponds to 72, Washington, D.C. also corresponds to 72, Charleston corresponds to 47, and Detroit corresponds to 74. Now this function would not be a one-to-one function because the value of 72 corresponds to two different cities. It corresponds to Austin and Washington, D.C. Next, we have the horizontal line test. This is a visual test that you apply to the graph of a function to determine if it's one-to-one. It states here if every horizontal line intersects the graph of a function at most once, then the function is a one-to-one function. Conversely, if it's possible to draw a horizontal line that intersects the graph more than once, then the function is not one-to-one. In the next example, we're going to apply the horizontal line test to determine whether each graph is a function. In example number 2, determine whether each graph is a one-to-one function and thus has an inverse. For part A, we have the graph of a parabola facing upward. All we need to do here to determine if this is a one-to-one function is apply the horizontal line test. Just drawing a horizontal line across the top of the graph, you can see that the horizontal line crosses the graph more than once, so this is not a one-to-one function. For part B, we have the graph of a cubic function. Applying the horizontal line test to this graph, you can see here that it's impossible to draw a line that crosses the graph more than once, so this is the graph of a one-to-one function. For part C, we have a straight line with a positive slope that crosses the y-axis at the y value of 1. If we apply the horizontal line test, it would be impossible to draw a horizontal line that crosses this graph more than once, so this is the graph of a one-to-one function. Moving on to part D, we have a horizontal line crossing the y-axis at the y value of 2. Applying the horizontal line test to this graph, the only place that we could draw a horizontal line is directly on top of the graph. This means that the horizontal line would intersect this graph at every single point, so this would not be the graph of a one-to-one function. For part E, we have the graph of a vertical line crossing the x-axis at the x value of -2. If we apply the horizontal line test to this graph, it would look like it passes. However, you need to be really careful because the horizontal line test only applies to graphs which are functions. A vertical line is not a function, so automatically it cannot be a one-to-one function. Moving on to part F, we have the graph in the shape of a V, but it's sideways and it's facing towards the right. Now if we apply the horizontal line test, it looks like it passes. However, we have the same problem as part E. This is actually not the graph of a function, so automatically this is not a one-to-one function. Next, we have the definition of the inverse function. It states here that the inverse of a one-to-one function f is the one-to-one function f inverse that consists of the set of all ordered pairs y, x, where x, y belongs to f. Essentially what they're saying here is all of the ordered pairs x, y that belong to the function f also belong to the inverse function except that the order is reversed. They're written as y, x. The next example demonstrates this property of inverse functions. For example number 3, find the inverse of the one-to-one function f, where f contains the set of ordered pairs 0, 1, -2, 7, 3, -6, and 4, 4. What we need to do here is find the inverse function of f. To do this, we're going to use the definition of the inverse function. All of the ordered pairs that belong in f also belong to the inverse function, except that the x and y coordinates are reversed. So for the answer, I wrote f inverse equals, and I have a set of curly brackets, and on the inside, I have the ordered pairs parentheses 1, 0, parentheses 7, -2, parentheses -6, 3, parentheses 4, 4. Next, we're going to go over the steps for finding the formula for the inverse function algebraically. Number 1, replace f of x with y. Number 2, interchange x and y. Number 3, solve for y. Number 4, replace y with f inverse of x. In the next example, I'm going to show you how we apply these steps to find the inverse function algebraically. In example number 4, determine whether the function f of x equals x plus 2 is one-to-one, and if it is, find f inverse. So if we take a look at the function f of x equals x plus 2, this is a linear function. This is just going to be the graph of a line with the y-intercept of 2 and a slope of positive 1. This means that the graph of this function would pass the horizontal line test. Next, we need to find the formula for the inverse function. We start off by replacing f of x with y, so we get y equals x plus 2. The second step is interchanging x and y. We get x equals y plus 2. The third step is solving for y. We need to get rid of the positive 2 by subtracting 2 from both sides of the equation. The result is x minus 2 equals y. Next, I flip the equation, so we have y equals x minus 2. The last step is replacing y with f inverse of x. So our final answer is f inverse of x equals x minus 2. Next, we have a practice problem. Determine whether the function f of x equals 2x minus 3 is 1-to-1, and if it is, find f inverse. Alright, so go ahead and pause the video, try out this problem, and then check back with the video to see the solutions. Alright, so let's go over the solutions. The first step here is to determine whether this function is 1-to-1. F of x is a linear function with a positive slope of 2 and a y-intercept of -3. This means that the graph of this function would pass the horizontal line test. So yes, this function is 1-to-1. Next, we need to find the inverse function. The first step is replacing f of x with y. We get y equals 2x minus 3. The next step is interchanging x and y. We get x equals 2y minus 3. Next, we need to solve for y. We need to get rid of the minus 3 by adding 3 to both sides of the equation. The result is x plus 3 equals 2y. Next, we get rid of the 2 in front of the y by dividing both sides by 2. We get x plus 3 divided by 2 equals 2y divided by 2. After simplifying, the result is x plus 3 over 2 equals y. Next, we flip the equation, so we get y equals x plus 3 over 3. The last step is replacing y with f inverse of x. Our final answer is f inverse of x equals x plus 3 over 3. For example number 5, graph the inverse of each graph. For part A, we have 3 points plotted on the graph, which are -5, -2, 0, 1, and 1, 7. We also have a 45-degree dotted line that goes through the origin. This line here is not part of the graph, but it's just there to help us graph the inverse function. Next, we graph the inverse function by using the definition. The inverse function contains all of the ordered pairs that are contained in f, except that the x and y coordinates are interchanged. So for example, this graph has -5, -2. That means the inverse function would have the point -2, -5, which I plotted on the graph over here. To get the rest of the points, we just repeat this process. So for the point 0, 1, the inverse will contain the point 1, 0, which I plotted over here. And for the point 1, 7, the inverse will contain the point 7, 1, which I plotted over here. So here is the graph of the inverse function in red. Notice here that the inverse function is just a reflection of the original graph reflected across this 45-degree dotted line. This is a property of all inverse functions. Moving on to part B, we have the graph of a line which goes through the points 0, -3 and 3, 3. We also have a 45-degree dotted line going through the origin, which is going to help us graph the inverse function. To graph the inverse function, we just follow the same steps as part A. We take the points from the original function, and then we interchange the x and y values to get the points for the inverse function. So for 0, -3, we get the point -3, 0 for the inverse function. And for the point 3, 3, this point would stay the same. So 3, 3 would also be part of the inverse function. Next, we draw a line going through our 2 points. And now we have the graph of the inverse function in red. Notice here that the graph of the inverse function is just a reflection of the original graph reflected across this 45-degree line. Again, this is a graphical property of inverse functions. You can use this property to double check that the graph of your inverse function is correct. If the inverse function is not a reflection of the original graph across the 45-degree line, then you know you need to go back and double check your graph. Next, we have a practice problem. Graph the inverse of each graph. For part A, we have the graph of the function f, which is just a line that starts at the point 0, 0 and goes through the point -1, 2 and continues on in that direction. For part B, we have the graph of a curve which starts at the point 3, 0 and curves through the point 4, 1 and continues on in that direction. Alright, so go ahead and pause the video, graph the inverse of each graph, and then check back with the video to see the solutions. Alright, so let's graph the inverse for part A. You should get the points 0, 0, and 2, -1 for the inverse function. Next, we draw a line going through those 2 points, and now we have the graph of the inverse function in red. For part B, you should have the points 0, 3, and 1, 4 for the inverse function. Next, we draw a curve through those 2 points, and now we have the graph of the inverse function in red. Next, we're going to go over composition and inverses. If a function f is 1 to 1, then f inverse is the unique function for which f inverse composed of f of x is equal to f of f inverse of x is equal to x, and f composed with f inverse of x is equal to f inverse of f of x equals x. According to this property, if you take the composition of a function and its inverse, the result after simplifying the composition will be x. In the next example, we're going to use this property to show that a set of 2 functions are inverses. In example number 6, show that each set of functions are indeed inverses. We have f of x equals 1 minus x over x, and f inverse of x equals 1 over x plus 1. To show that these functions are inverses, we're going to take the composition of f composed of f inverse of x and f inverse composed of f of x. Starting with f composed of f inverse of x, we get f of f inverse of x. F inverse of x is just 1 over x plus 1, so we have f of 1 over x plus 1. From here, we substitute in 1 over x plus 1 into the function f everywhere we have an x. So we have 1 minus parentheses 1 over x plus 1 divided by parentheses 1 over x plus 1. Next, we could drop the parentheses, and now we need to combine the 1 minus 1 over x plus 1 in the numerator. To do this, we change the 1 to have a denominator of x plus 1, so we multiply the 1 by x plus 1 over x plus 1. The result is x plus 1 over x plus 1 minus 1 over x plus 1 divided by 1 over x plus 1. Now we could combine the fractions in the numerator. We get x plus 1 minus 1 over x plus 1 divided by 1 over x plus 1. Next, we simplify the fraction in the numerator. The plus 1 and the minus 1 will cancel out, and we get x over x plus 1 divided by 1 over x plus 1. Next, to simplify this complex fraction, we take the fraction in the numerator and multiply it by the reciprocal of the fraction in the denominator. We get x over x plus 1 times x plus 1 over 1. From here, we could cancel out the x plus 1's. The final result is x. Since the final result of the composition is x, everything seems to be correct. Now we also need to check the inverse of f composed of f of x. We get f inverse of f of x. F of x is just 1 minus x over x, so we have f inverse of 1 minus x over x. Next, we substitute 1 minus x over x into the inverse function everywhere we have an x. So we get 1 divided by parentheses 1 minus x over x plus 1. Next, we just drop the parentheses, and then we need to simplify the denominator. We need to rewrite 1 as a fraction with the LCD of x. To do this, we just multiply the 1 by x over x. The result is 1 divided by 1 minus x over x plus x over x. From here, we need to combine the fractions in the denominator. So we get 1 divided by 1 minus x plus x over x. From here, we simplify the fraction in the denominator. The minus x and the plus x cancels out. The result is 1 divided by 1 over x. Next, we simplify the complex fraction by taking the numerator 1 and multiplying it by the reciprocal of the denominator, x over 1. We get 1 times x over 1, which simplifies to give us x. Okay, so after simplifying both compositions, the result was x. This shows that both functions f of x and f inverse of x are indeed inverses. Next, we have a practice problem. Show that each set of functions are indeed inverses. We have f of x equals 2x plus 1, and we have f inverse of x is equal to x minus 1 over 2. Alright, so go ahead and pause the video, try out this problem, and then check back with the video to see the solutions. Okay, so let's go over the solutions. First, we'll start with f composed of f inverse of x. We get that this is equal to f of f inverse of x. F inverse of x is just x minus 1 over 2, so we have f of x minus 1 over 2. Next, we substitute in x minus 1 over 2 into the function f. We get 2 times the parentheses x minus 1 over 2 plus 1. Next, we could simplify by canceling out the 2's. The result is x minus 1 plus 1. From here, the minus 1 and the plus 1 cancels out, and the final result is x. Next, we do the composition, f inverse composed of f of x. This is equal to f inverse of f of x. F of x is just 2x plus 1, so we get f inverse of 2x plus 1. Next, we substitute in 2x plus 1 into the inverse function. We get parentheses 2x plus 1 minus 1 divided by 2. From here, we could drop the parentheses and then simplify. In the numerator, we have plus 1 minus 1 will cancel out, and we get 2x over 2. Next, we cancel out the 2's, and the final result is x. Because both compositions resulted in x after simplifying, this shows that both functions f of x and f inverse of x are indeed inverses. Okay, well this wraps up our video. Thank you very much for watching. I'm Professor Diwa, and I'll see you in the next one.